Hi there. This is exam number 2 by Johnny Murphy. I'm sorry I won't be able to have my face. I don't have a good face recording system. But yeah, getting into it. Problem 1. Basically, we're asking what happens if we have a feed temperature that's going to be increasing over time, then decreasing over time afterwards, and then we have a big tank that's going to be in there. I would like to make 4 different points here, A, B, C, and D. A is starting to increase until B, and that's going to be representing how the temperature is going to be looking overall until we reach that point B. And as soon as we reach point B, we're going to go ahead and get a skyrocket to point C. But it's not going to increase or decrease exactly like how we would like it to, because it's not going to follow the same path. We're going to go ahead and see a slow deterioration until point D, where it's going to go ahead and drop off and deteriorate. And this is the reasoning behind it is we went over in class with like a intersection of all the t's with other t naughts, and there's points that are realistic and points that are unrealistic. And so we can look at this. All the points on this graph are going to be realistic, but the points in the middle are going to be unrealistic. But yeah, so that's going to be increasing A, B to C, and then it's going to start decreasing down to D, and then back to A. So moving on to problem 2, we're going to go ahead and start with Tn to T1, and it's going to be a linear relationship to the amount of heat that's lost to T2, and there's no phase change, there's not going to be a flat line or anything like that, there's not going to be any ridiculous changes, it's going to be all linear, and then we're going to go ahead and move on to the reactor, which is going to follow the same shape and path as the conversion. And so we're going to see this kind of like S-shape conversion, and it's going to go ahead and move up till TLR, and TLR is going to be fed back into the heat exchange, where we're going to see the same proportional loss in heat as we had gain in heat in T1, and it's going to come back out at the higher temperature because of the reactor being an exothermic reaction. Moving on to 3C, we're going to go ahead and it's going to ask us why the selectivity of C to A is going to be negative, and why it happens at some points in the reactors, and what would happen if there's E plus B to D instead of A plus B to D. And I'd like to say, no, my answer is selectivity is negative because as the reaction starts, we're going to go ahead and see that the second reaction isn't going to be in play. But as soon as the second reaction starts being in play, we're going to see some more and more. Sorry, let me go ahead and restart. So basically, reaction 1 is going to be losing A, or removal of A with a creation of C. So the selectivity itself, by definition, is going to be the creation of C over the removal of A. So if we have the creation of C being put in the reverse direction due to the increase of partial pressure of B, then we're going to go ahead and swap the direction of reaction 1. So that means that the consumption or the creation of C is actually going to be negative because it is being consumed to produce A. Now, producing A would be keeping the same sign for selectivity if there wasn't reaction 2, which reaction 2 is going to be instead a removal of A to produce some other chemicals we're not really interested in. So that answers kind of the second part of the question, where the selectivity of C to A wouldn't be negative if we replaced E plus B to D, because there would be no removal of A. So if the reaction 1 flipped to the reverse direction, then that would mean that if they flipped, then the consumption of A would be instead negative because it's a production of A, while the production of C is going to be it's two negatives. They cancel out to be a positive. That's all I'm trying to say. And I swear it's like the 30th recording that I can't. Oh well, whatever. You get what I mean, I think. Okay, moving on to part D. Basically, which reactor, 1 or 2, is the pressure drop more significant? And we can see that it's going to be reactor 1 because the gradient of the negativity of the selectivity here is going to be drastically larger, and that matters because of the partial pressures. So the partial pressures have a high impact especially with the cubic function with PC also on top, that as soon as we have higher pressure, we're going to see a drastic change in whatever we have. So right here we have 1 to negative 0.8. but here we have 1 to negative, or to negative like 6. So that means that we're going to have a higher pressure difference, especially when there's a progression in the reaction due to like higher weight of catalyst. So what that means for problem D is that since there was a larger drop in reactor 1, we know that there's going to be a larger pressure drop. There's a larger drop of selectivity in the negative, so that means that there's going to be a larger pressure drop. And again, it's like basically you can go over here, it's like third order dependence. So that means that we're going to see a high relationship between the two. So kind of going hand in hand with that, which reactor is going to have a higher yield of C? So if we have more and more of, if we have a higher dependence on the on the reactor 1 on the pressure, then we can see that as soon as it flips in the negative direction, then goodness gracious, I am brain farting all of a sudden. Oh man. Okay, so sorry. Reactor 2 will have a higher yield than C because you'll have less of reaction 1 going in a negative direction or in the reverse direction. So because the pressure dependence is so high in the first reaction that if we have a lot of B that's produced, then it's gonna be very soon to reverse the direction and start removing C from reactor 1 to produce more A. So if we have a lower pressure, if we have a lower pressure drop, then that means that there's gonna be less and less dependence on that PB. So then there'll be less and less of that reaction 1 going in the negative direction or the reverse direction. Yeah, so I think that's basically it on that question. I can come back to it, I guess, if need be. 4A. So would you expect the Knudsen or the molecular diffusion coefficient to be larger? I said the Knudsen because the particle diameter is much greater than the pore diameter. And so that means that there's going to be a lot more interactions with the wall to the particle than other particles to the particle. Yeah, that's basically it, because I mean Knudsen is a wall-based diffusion or wall-based coefficient, while molecular diffusion is going to be a more bulk diffusion coefficient. So moving on to problem, oh no, we have to do D, never mind, or B. Going to 5B to C, it's going to ask if the flow rates are dependent on the dT/dV, and I said yes, because no matter what you change, dT or dV, then there's going to be a change in the reaction, and the change in the reaction is going to cause a change in the flow rates. So the reaction itself is like A plus B to C. It doesn't really matter. But as the volume proceeds, that means more and more of the reactor is going to be proceeding over. So that means that A and B are going to be decreasing and C is going to be increasing. And vice versa with DT. DT is going to change the whole entire reaction. It's going to change how fast or how much the reaction proceeds and all the rate constants going with it. So that means that this bottom part needs to be dependent on dT/dV and needs to be changing. It can't be the initial. And also, notation doesn't have a not, so that's good reasoning. Okay, so moving on to the overall heat coefficient over the diameter. I mean, it doesn't really. I initially guessed 8,000. It was too high of a conversion. Dropped down to 6,000. Too low of a conversion. You know how it is. It kind of like bounces in between. Got 6,453 with a maximum of 346.6 Kelvin. I noticed that the reaction only increased in temperature, so the very end temperature was the highest temperature. And kind of explaining what this all means is that as the conversion increases, that means that the reaction is proceeding because it's not reversible reaction. As the conversion increases, that means that because it's an endothermic reaction, because of the you can see the heat of reaction being this large number, that means that more and more heat is going to be required to be put into the system. So yeah, that's basically the reason is that like the overall heat coefficient has to increase with conversion because more and more heat has to be required to be put into the system. All this beautiful numbers. Yeah, so basically that's it. I mean, problem 3 is kind of a little sketchy, but I hope that you understand what I meant to translate over. I mean, basically, I'm just trying to say that over time, because of the pressure dependence, the selectivity is going to, the reaction 1 is going to start going in the negative direction, while reaction 2 is going to keep on going in the forward direction. So that means that A is still going to be consumed in the bottom reaction, while in the first reaction, A is going to initially be consumed, but then start going in the negative reaction because there's a high pressure dependence. Thank you very much. That is my time. Have a good day.